Welcome to G Fun Facts Online, where we dive deep into the science shaping our world. Today we're talking about one of humanity's most fundamental challenges: securing clean water for a growing planet. The statistics are sobering. Billions lack access to safely managed drinking water, and our rivers, lakes, and oceans are increasingly choked with a chemical cocktail of pollutants. But what if I told you that a powerful hero in this fight is emerging from an unexpected place? It's not a complex chemical or a billion-dollar piece of machinery. It's a humble, black, carbon-rich substance that you could, in theory, make in your backyard. It's called biochar, and it's revealing a hidden superpower that could revolutionize how we purify our most precious resource. For a long time, we've known biochar as a sort of super compost, a way to enrich soil and fight climate change. But its story is getting much bigger. Scientists are discovering it can act as a dynamic, active warrior against water pollution, and it's changing everything we thought we knew about this ancient material. So, what exactly is this stuff? The idea isn't new at all. In fact, it's ancient. Thousands of years ago, in the Amazon basin, indigenous communities created something archaeologists now call terra preta, which is Portuguese for dark earth. They would systematically add charred organic matter, like bones and plant waste, into the notoriously poor Amazonian soil. The result was a shockingly fertile black soil that remains productive even today, thousands of years later. It was an agricultural marvel, a testament to the incredible, long-lasting power of this special charcoal. Fast forward to the 21st century, and we're rediscovering this ancient wisdom with a modern scientific twist. Today, we produce biochar through a process called pyrolysis. Now that sounds technical, but the concept is simple. Imagine taking a bunch of organic waste, things like wood chips, leftover corn stalks, rice husks, manure, even sewage sludge, and putting it inside a container with very little to no oxygen. Then, you heat it up to very high temperatures, anywhere from 300 to 700 degrees Celsius. Without oxygen, the material can't burst into flames. Instead, it thermally decomposes, transforming into three useful things. First, you get bio-oil and syngas, which can be captured and used as renewable energy. Second, and most importantly for our story, you get biochar. This process turns flimsy plant matter into a stable, incredibly porous, and carbon-dense form of charcoal. It's a perfect example of the circular economy in action, taking waste streams that would otherwise rot in a landfill and releasing greenhouse gases, and turning them into multiple valuable resources. What's fascinating is that we can tailor the properties of biochar by tweaking the recipe. By changing the temperature or the heating rate during pyrolysis, we can create different flavors of biochar. Generally, the hotter you cook it, the more pure carbon it contains, and the more intricate its internal pore structure becomes. And it's that structure that holds the key to its water-purifying magic. So how does a piece of charcoal actually clean water? For a long time, we thought it was just a simple sponge, but the reality is far more sophisticated. Biochar's primary weapon is a process called adsorption. Don't confuse this with absorption, where a sponge soaks up water. Adsorption is when molecules of one substance, like a pollutant, stick to the surface of another, like biochar. And biochar has a truly mind-boggling amount of surface area. Thanks to the pyrolysis process, it's riddled with a complex network of microscopic tunnels and pores. To put it in perspective, a single gram of biochar, about the weight of a paperclip, can have an internal surface area that's larger than a football field. It's this vast, intricate landscape that acts like a sticky trap for a huge range of contaminants. Think of it as a high-tech molecular magnet. What can it catch? First, there are the heavy metals. We're talking about toxic stuff like lead, cadmium, arsenic, and mercury. These metals can cause severe health problems and devastate ecosystems. Biochar can grab onto them through a few clever mechanisms. One is ion exchange, which is like a tiny trading post on the biochar surface. The biochar might have harmless ions, like calcium, that it's willing to trade for the more toxic heavy metal ions in the water. Another way is through precipitation, where the biochar's surface chemistry encourages the metals to form solid, insoluble particles, effectively taking them out of circulation. Then you have the organic pollutants. This is a massive and growing category of contaminants. It includes everything from pesticides and herbicides washing off farm fields, to pharmaceuticals and personal care products that go down our drains, to industrial chemicals like polycyclic aromatic hydrocarbons, or PAHs. Biochar's carbon-rich surface has a natural affinity for these carbon-based molecules, pulling them out of the water through forces like hydrophobic interactions and hydrogen bonds. Finally, it can tackle nutrients, specifically nitrogen and phosphorus from agricultural fertilizers and wastewater. While these are essential for life, too much of them in our waterways leads to eutrophication. This is when you get massive algal blooms that suck all the oxygen out of the water, creating vast aquatic dead zones where nothing can live. Biochar has shown it can absorb these excess nutrients, helping to prevent this widespread environmental disaster. This adsorption ability alone makes biochar an incredibly useful tool. But this is where the story takes a turn, revealing what scientists are calling its hidden superpower. For years, the scientific community believed that biochar was just a passive filter, a sponge that just soaked things up. But groundbreaking recent research has shown that it's so much more. Biochar can actively destroy certain pollutants. The process is called direct electron transfer. This discovery fundamentally elevates biochar from a passive janitor to an active environmental warrior. Here's how it works. Instead of just trapping and holding on to a harmful organic pollutant, the biochar can act as an electron donor. Certain features on the biochar's surface, like specific carbon-oxygen groups and its graphitic structure, can create pathways for electrons to flow. The biochar literally shoots electrons at the captured pollutant molecule. This jolt of energy is enough to break the chemical bonds holding the pollutant together, shattering it into smaller, simpler, and far less harmful substances. It's a microscopic demolition crew that works without needing any additional chemicals or energy inputs. And this is not just some minor niche effect. Studies have found that this direct degradation can be responsible for up to 40% of the total pollutant removal. It's a powerful, previously overlooked mechanism that makes biochar dramatically more effective than we ever realized. This changes the game completely. We're not just storing pollutants on a filter that we then have to deal with later. In many cases, we're actively destroying them on site. The story of biochar's benefits doesn't even end there. Its production and use create a cascade of positive environmental impacts that make it a truly holistic solution. We've already touched on the circular economy aspect. The ability to make biochar from agricultural waste, forestry residues, and even municipal sewage sludge is revolutionary. In a world struggling with overflowing landfills, this technology offers a way to not just manage waste, but to valorize it, to turn a problem into a solution. Every ton of biomass converted into biochar is a ton that isn't decomposing and releasing methane, a greenhouse gas far more potent than carbon dioxide. But perhaps the most compelling co-benefit is its role as a climate change ally. The very process of creating biochar is a powerful form of carbon sequestration. Let me break that down. As a plant grows, it pulls carbon dioxide from the atmosphere through photosynthesis to build its tissues. If that plant dies and decomposes naturally, almost all of that carbon is released back into the atmosphere as CO2. It's a short-term cycle, but when we take that plant matter and turn it into biochar through pyrolysis, about half of that original carbon gets locked into an incredibly stable, crystalline structure. This isn't like the carbon in a piece of wood, which will rot away in a few years. The carbon in biochar can remain stable for hundreds, even thousands of years. So when we use this biochar, whether in a water filter or later added to soil, we are effectively taking that carbon out of the atmospheric cycle and burying it in a safe, stable form. This makes biochar a carbon-negative technology. It actively removes more carbon from the atmosphere than is produced during its creation and transport. Some projections suggest that a global, sustainable biochar industry could potentially offset up to 12% of total annual greenhouse gas emissions. That is a staggering number. It means that while we're cleaning our water, we're also actively fighting climate change. This all sounds great in a lab, but is it actually being used in the real world? The answer is a resounding yes, and the applications are incredibly diverse. Let's look at industrial wastewater. Many industrial processes, like metal plating or mining, produce wastewater laden with a nasty cocktail of heavy metals and toxic organic compounds. In one case study, commercial biochar was used to treat wastewater from a plating facility. It successfully removed high concentrations of heavy metals, proving its worth in a demanding, high-stakes environment. In another fascinating study, researchers created a special nickel-augmented biochar using eggshells and waste sludge. This designer biochar proved highly effective at cleaning up produced water from oil and gas operations, which is notoriously difficult and expensive to treat. Then there's stormwater management. When it rains in a city, the water that runs off our roads, parking lots, and roofs carries a ton of pollution with it. Oil, gasoline, heavy metals from brake dust, and more. This runoff is a major source of pollution for our rivers and lakes. Engineers are now integrating biochar into stormwater management systems like rain gardens and filtration trenches. Research at Oregon State University, for example, demonstrated that filter mixtures containing biochar could remove over 95% of dissolved copper and zinc from typical stormwater runoff. It's a simple, passive way to clean up our cities every time it rains. But perhaps the most inspiring applications are in community water purification. In many rural and developing communities around the world, access to clean drinking water is a daily struggle. Biochar offers a potential lifeline. Because it can be made from local agricultural waste using relatively simple technology, it provides a low-cost, decentralized solution. Organizations like Aqueous Solutions have been pioneers in this field, helping communities build and maintain simple water filtration systems that combine layers of sand, gravel, and, critically, biochar. These filters have proven to be effective at removing turbidity, bacteria, and other contaminants, providing safe drinking water using locally sourced, sustainable materials. Now, as with any emerging technology, the road ahead is not without its challenges. Biochar is not a magic bullet, at least not yet. One of the biggest hurdles is consistency. The properties of biochar can vary dramatically depending on what you make it from, the feedstock, and the precise pyrolysis conditions. Biochar made from coconut shells at 700 degrees will behave very differently from biochar made from chicken manure at 400 degrees. This variability makes it hard to standardize performance, which is critical for engineers and regulators. The cost of production can also be a barrier. While it's generally cheaper than its industrial cousin, activated carbon, the initial investment in pyrolysis equipment can be significant, especially for large-scale projects. And while the lab results are incredibly promising, we still need more long-term, field-scale studies to fully understand its effectiveness and economic viability in different real-world scenarios. But the future is incredibly bright, and innovation is happening at a blistering pace. Scientists aren't just using biochar. They're engineering it. They are creating designer biochars, modified to target specific pollutants with ruthless efficiency. This can involve impregnating the biochar with materials like iron or magnesium oxides, which act like specialized magnets for pollutants like phosphorus or arsenic. Other modifications involve activating the biochar with steam or acids to further increase its surface area and absorption power. Researchers are also exploring hybrid systems. Imagine a water treatment process that combines a biochar filter with another technology, like a membrane filter or an advanced oxidation process. These multi-stage systems could achieve a level of purification that neither technology could manage on its own. And with every new study, our fundamental understanding of the mechanisms, like that amazing direct electron transfer, grows deeper. This knowledge will allow us to design and deploy biochar applications with ever-increasing precision and efficiency. Biochar's journey is a remarkable one. It has traveled from an ancient soil amendment in the Amazon rainforest to a cutting-edge material at the forefront of environmental science. Its ability to not only clean our water but to do so while turning waste into a resource and sequestering carbon makes it a uniquely powerful tool for a world grappling with the interconnected crises of pollution, resource scarcity, and climate change. As we continue to unlock the full potential of this unassuming black carbon, its role in our quest for a sustainable future will only grow. The hidden superpower of biochar is a secret no more, and its impact is just beginning to ripple across the globe, heralding a new and hopeful chapter in the story of environmental stewardship. Thanks for tuning in to G Fun Facts Online. Join us next time as we explore another fascinating piece of the world around us.